All right, so let's work on the inner product problems. Um, so the first couple here, we're assuming we have an inner product. So you're just implementing problem number one. If I take the inner product of u and v, I'm going to end up with 2 times 8 times 8 plus 3 times 0 times 3 plus negative 8 times 16. These reduce to 128, 0 and negative 128. So the whole inner product becomes 0. So later on, we're going to show that this has some sort of meaning as far as orthogonality, but we're going to leave it there for right now. Number 2, we have u, the inner product of u and v. So let's take 8 times negative 5 plus 2 times negative 3 times 4 plus negative 1 times 9. So this is going to be negative 40. This is going to be negative 24. And this becomes negative 9. So the whole inner product there is negative 73. Let's take a look at number 3. This is where we start defining an inner product with functions. So this is going to be the integral from negative 1 to 1 of x squared times x squared plus 1 dx. Excuse me, the integral from negative 1 to 1 x to the 4th plus x squared dx. So this is 1/5 x to the 5th plus 1/3 x to the 3rd from negative 1 to 1. That's going to be a 5th plus a 3rd minus negative a 5th minus a 3rd. Right, so this is going to become 2/5 plus 2/3, which is 6/15 plus 10/15, which is 16/15. Okay, so let's move on to number 4. All right, number 4 is again an inner product of two functions on the interval from negative 1 to 1. So we're going to take the integral from x e to the x dx. So this is a by parts problem. Let the u be the x. Let dv be e to the x dx. This means du dx is 1, which means du is dx. Take the integral here, and you're going to end up with v is e to the x. So this is like the by parts scratch work. You take u times v, x times e to the x from negative 1 to 1, minus the integral of v du from negative 1 to 1. Put 1 in there, you're going to get e. Put negative 1 in there, you're going to get minus negative 1 over e. Okay. So now this becomes minus e to the x from negative 1 to 1. This is e plus 1 over e minus e minus 1 over e. So that comes out as 2 over e. All right, so a little bit of integration by parts just to keep you on your toes there. Let's look at number 5. Okay, number 5 is taking the inner product of two matrices. So this is going to give me 2 times negative 1 times 0 plus 3 times negative 2 plus 4 times 1 plus 2 times negative 2 times 1. So it's 0 minus 6 plus 4 minus 4 just gives me negative 6. All right, so let's look at number 6. It's again an inner product of two matrices, but this time I get like 2 times 1 times 0 plus 0 times 1 plus 0 times 1 plus 2 times 1 times 0, and each of those terms has a 0 in it, so that's 0. number 7, we're working with polynomials. So this is going to yield 1 times 0, because there's no constant term in the Q, plus -1 times 1, plus 3 times -1. So this is 0 minus 1 minus 3 gives me -4. Let's look at number 8. 8 is also polynomials, so P times Q here is giving me 1 times 1. We have no linear terms, so it's 0 times 0. And then the quadratic terms are giving me 1 and -1. So this is 1 plus 0 minus 1. Means these things are, again, have some semblance of orthogonality. Now, we get to disprove some things as being inner products. So let's see how that works. So remember that disproving is always easier than proving. You just need one counterexample. In number 9, if I let u be the vector 0, 1, and I use that product on itself, that's going to give me the value 0, but u does not equal 0, the 0 vector, so this implies that I'm not an inner product, because I get the inner product can be 0 if and only if u can be the 0 vector. So let's look at 10. 10, I disproved this by letting u be the vector 6 radical 6, because then the inner product of u with itself becomes 6 times 6 minus 6 times the square root of 6 times the square root of 6. This is 36. This is also 36. So that's 0. And again, u is not the 0 vector. And I'm only supposed to get 0 if u is in fact the 0 vector, which it is not. All right, so to disprove number 11, I just let u be 1, 1. I let the v vector be 2, 2. And then I looked at, what do I get if I take 3u times v? Okay, so that's going to give me 3, 3, right? So this would be 9 times 4 plus 9 times 4. So if I look at that, that's 9 times 1 times 4 plus 9 times 1 times 4, which would be 9 times 1 times 4 plus 1 times 4, which is 9 times the inner product, or the product of u and v. It's not an inner product, which is not equal to 3 times the product of u and v, which should be true if I have an inner product. So that violates this associative property here, right? So now let's look at number 12. Okay, so the way we broke number 12 was to let u be 1, 2, let v be 3, 4, and then we looked at, what do I get if I take u times v? If I take u times v here, I should get 3 times 1 times 4 plus 2 times 3, and this is 12 plus 6, which is 18. If I take v times u, I get 3 times 2 times 3 plus 1 times 4. This is 18 plus 4, which is 22. And 18 does not equal 22, so u times v does not equal v times u. And you have to have commutative property in order to have an inner product. So that one doesn't work either. So there's your solutions to the inner product problems. If you have further questions, drop them in an email, show up in one of the drop-in sessions, and we'll go from there. I hope you're all well. Thank you.